Okay, here we go. We're catching up on curve sketching, so we want to do this stuff. Some of you guys said you had questions about your assignment. How about this? Raise your hand if you've completed at least a couple problems from this assignment. Feel good about it. Okay, so the rest of you, let's make sure we follow along. This can be challenging. Miss. Okay. We really set up three kind of sets of areas to work in here. And the first one I'm going to set up is we are going to look for the intercepts. Let's start by looking at our function 2 plus 4x squared minus 2x to the fifth. Can anybody tell me what the y-intercept is just by looking at it? 2. If you plug in 0 for x, you get 2 for y. So 2 would be our y-intercept. How do we find the x-intercept? Plug in 0 for the function value. Whoop. And we get 0 equals 4x squared. I'm sorry, 2 plus 4x squared minus 2x to the fifth. Now, I want you to know that we currently can't solve that. If it was to the second degree, you could use the quadratic formula, correct? There is an equation that you can use to solve a cubic. However, it's about a full page in length. And there is a formula you can use to solve the quartic. It's about 2 to 3 pages in length. There's no equation that we really have that in fact, it's been proven that you can't solve a fifth degree, perfectly. You can't. And it's a very interesting story. Newton, we're going to come up with this. Newton had a method. Section 4748 is called Newton's method. He finds a way we can use calculus to estimate them very carefully. But so here we just gotta say give up. We can't really do that. Sure. Yeah. And then we're done. So. Well, but you guys, if you remember before, we were limited to this. If you wanted to find the shape of a polynomial, you are limited to finding the zeros of the polynomial. And we can't find them, but we can find the first and second derivative, which tell us, boys and girls, which tell us a lot more about the shape. So let's just write a question mark there and move on to the first derivative. We plug in 0 for x. If we plug in 0 for f prime of x now, what is the derivative? Good. 8x minus 10x to the fourth. Is that something that we can solve? We sure can. Let's factor out a 2x. And you're left with 4 minus 5x to the third. Kelly, question? No? Okay. So we set both of these pieces equal to 0. 2x equals 0. And 4 minus 5x to the third equals 0. What is one of my solutions? 0. And the other one, I'm going to just write 4 equals 5x to the third. If I add that to the other side, divide by 5 and take the cubed root, I end up with the cubed root of 4/5 is equal to x. So that we have a better understanding of what that actually means, let's convert it to a decimal. The cubed root of 4/5 is equal to 0.93. So we have 0 and 0.93. I'm going to use my number line now. Do I put this number line on top or on bottom? Top. First derivative I put on top. So we have 0 and 0.93. Let's do the second derivative while we're at it right away. I'm going to take the second derivative and set it equal to 0. What is the derivative of 8x minus 10x to the fourth? Very good. I can solve that by 40x to the third is equal to 8. 8 over 40 reduces to 1/5. So x is equal to the cubed root of 1/5. Let's convert that to a decimal. We get 0.58. Does that go on the top or the bottom? Put that one on the bottom, so I have 0.58. Approximately right there. The reason why I make the number lines is because I want to do what we refer to as interval testing. I want to test the intervals to determine intervals of increasing, decreasing concavity. I want to use them to find local maxes, mins, inflections, information like that. So let's begin our interval testing. Let's start at the top. Does the first derivative tell us concavity or increasing and decreasing? Right, and so I look at my first derivative, which is right here, and I can plug in a number to the left of 0. What number would you like to plug in? Okay, if we plug in -2, you get, let's see, -16 minus 2 to the 4th is going to be 16. So you've got -16 minus 160. Is that going to be positive or negative? Negative. If we plug in -2 into this, if you know, you could plug in -1. That might be a little bit easier. If you're not confident about your calculation, go ahead and type it into your calculator. But what's the number between 0 and 0.93 you could plug in? 0.5. What's 1/2 of 8? 4. Come on in. Okay, if we plug in 0.5, we get 4. Minus, again, we plugged in 1/2. What's 1/2 to the 4th? 1/16. So 4 minus 10/16. Is that going to be positive or negative? That's going to be positive. You don't even actually have to calculate it. Just know that it's going to be positive. So we have negative, positive, and then what's the number to the right of 0.93 you can plug in? 1. You would have 8 minus 10, which is? It's negative. Okay, so we can now identify our intervals of increasing and decreasing. Tell me where I'm increasing. 0 to 0.93. Decreasing. Good. In order to check for concavity, I have to test the bottom. What's a point to the left of 0.58 I can plug in? 0 is a great number to plug in. 8 minus 0 will be positive, so I am concave up. Okay, now let's plug in a number to the right of 0.58. Let's plug in 1. 8 minus 40, positive or negative? Negative, so you can see you're concave down. So there's my intervals right there. We're going to be concave up from -infinity to 0.58, concave down from 0.58 to infinity. We're now ready to determine our points of inflection and concavity local max and local mins and inflection points. So where the first derivative is equal to 0 is where I might have a local max or local min, okay? So I'm going to check the 0 spot. Am I concave up or concave down at 0? Up. So therefore, does it have to be a local max or local min? Local max. If I'm concave up, I have a local max. So I will have a local max at 0, some y value. Oh, I'm sorry. Yep. If you're going to be a local max, you're concave down. If you're going to be a local min, you're concave up. So I'm concave up. Here I'm concave down, so I must have a local max at 0.93. And the inflection point will be at 0.58. I need y values for these because then I can actually sketch its behavior. So let's take out our calculator. Let's picture a meteora. So we have 2 plus 4x squared minus 2x to the 5th. If I go to my table, I'm going to plug in 0.93. I get 4.07. Plug in 0. And we get 2. We knew that. Plug in 0.58. And we get 3.21. So that's what I have. Do I have any spots in this polynomial where it's undefined? Is there any number I can't plug in? No, so you don't have any vertical asymptotes. And it's not a rational function, so we actually don't have any horizontal asymptotes either. But we do have what we call end behavior, and that's what I'd like to end with. In order to find the end behavior, I find the limit as x approaches. Yep, infinity. Of 2 plus 4x squared minus 2x to the 5th. What would you like to take out of that to find the limit? Let's take out an x to the 5th. So we'll have the limit as x approaches infinity of x to the 5th times 2 over x to the 5th plus 4 over x to the 3rd minus 2. As we allow this to go to infinity, what happens inside the brackets here? These go to 0. 0 plus 0 minus 2 is negative 2. So you end up with negative 2x to the 5th. So let's think about that. As you approach infinity, if you plug a very, very large number into this, what are you going to get out? A very large negative number. So, as far as the end behavior, you could say as x goes to infinity, y goes to negative infinity. What if we allowed x to go to negative infinity? What would y go to? It goes to positive infinity. In fact, I want you guys to understand that this is what the function models in its end behavior. If we were to graph both negative 2x to the 5th as well as 2 plus 4x squared minus 2x to the 5th, as we got closer and closer to infinity, they would start to actually overlap one another. It would be very close to where they would match up. So that's the behavior we'd like to show. So just having a little thought about that. All right, let's plot our points so we'll get a very accurate sketch of this graph. So it looks like I'm going to put a 1 over here. Thank you. Make that graph. Greta. Another Greta. Katie. That was easy. They are popular. Okay. All right, I'm going to plot the points. I'm going to start by plotting. I don't know any of my x-intercepts. I know my y-intercept is 0, 2. I have a local max at 0.93 and 4.07. So 0.93 and 4.07, so right about there. Maybe just a tad too high. Try again. Okay, then we have a 0.58 and 3.21. That's all I have for points. So how do we begin to sketch something like that? It comes from up top, and we know that this is a local min. We change concavity there. Now you might say that that looks more like a cubic. Sometimes 5th degrees can look like cubics. If I make my window -2, something very similar to what we have. Devin, did you have a question? Yeah, exactly. Something very similar to that on your last test. What did I do? Oh, I switched up my min and my max. And so if you ever want to check your answers, this is where you go to. Just go to your graph. Is that an accurate depiction? It's very, very similar. And so we look at that and we say, all right, that's pretty good. It's pretty good. So that's a polynomial. We're going to do one more now that's a rational function. And no new assignment. You just continue through with the one that you had. Any questions on this? Okay, one more. Boys and girls, shh. This one's going to take a while to get through. Okay, this one's a little bit more complicated. Okay, let's look at the asymptotes first of all. Okay, because this is not a polynomial, you can tell right away that we might have some vertical asymptotes, horizontal asymptotes, some behavior like that. So let's see if we can figure that out. Okay, where is it undefined in the denominator? Or -2. 4 minus x squared equals 0. You could factor that to be 2 minus x times a 2 plus x. So you would have a 2 and a -2. So we have vertical asymptotes of x equals +2 and x equals -2. I'm going to wait to sketch that until I get a little bit more knowledge of my other points here. Horizontal asymptotes, those will happen as x approaches infinity. So let's try to evaluate this limit. We'll do the limit as x goes to infinity of, what do I have on top, 4x? 2x. I haven't actually done this problem before, so. No, it won't come out incorrect. I'm just not real familiar with it. So we're going to take this as it goes infinity. What should I take out of the top? An x, which just leaves us with the 2x. What should I take out of the bottom? X squared. And I get 4 over x squared minus 1. Allow x to go to infinity. Or to a very large number. Very good. You're going to get 2x over -x squared, which reduces to -2 over x. As x goes to positive infinity or negative infinity, doesn't matter. You're going to get a small number over a very, very large number. It goes to 0. So we do have a horizontal asymptote of y equals 0, or the x-axis. Okay? So our work with limits as x approaches infinity verifies that for us. We know exactly what the behavior will be. Again, by seeing that the larger degree is in the denominator, you could tell right away that it's going to go to 0. So that would be a hint to you right away. But on your test, you must verify it. Okay. All right. So now we go from here. Let's try x and y intercepts. The y-intercept occurs where x is equal to 0. If x is equal to 0, everything's 0. All right. The x-intercept will happen where the top is equal to 0. Where is the top equal to 0? 0. It crosses the origin. It crosses at 0, 0. Let's go about finding our derivatives. F prime of x is equal to, what is the derivative of the top? 2 times the bottom left alone, which is 4 minus x squared, minus the top left alone, 2x, times the derivative of the bottom. What's the derivative of the bottom? -2x. over the bottom squared, 4 minus x squared quantity squared. So that means that f prime of x is then equal to 8 minus 2x squared plus 4x squared. That's okay. So I end up with, it looks like 2x squared plus 8, correct? Over 4 minus x squared quantity squared. Oh boy. We're wondering where it equals 0, right? That's where the top is equal to 0. Actually, we do need to test, we really need to look for all critical points at this spot. We do want to look for where it's equal to 0, but obviously, where is it undefined? Positive 2 and negative 2. Have we already accounted for that? Yes. So now let's look at the top. 2x squared plus 8 equals 0. Is there any solution to that? No, it's imaginary. So therefore, what do you know? Nathan sees it, okay? The top is always positive. Okay, think of this picture, this graph, 2x squared plus 8. It's always above the x-axis. The bottom, you're squaring it. Is the bottom always positive? Yeah, so you have a positive over a positive, which is a positive. So it's always positive. You have no local maxes, you have no local mins, and it is always increasing. Very smart, Mr. Nathan. Does anybody have questions how we come up with that? Do you see that? Okay, we'll try one more time. You take the top, you set it equal to 0. 2x squared plus 8 equals 0. Whether you use the quadratic formula or whether you try to factor or subtract the 8 and solve, any way you do it, you're going to come up with an imaginary solution. So that means that nowhere can this be equal to 0. So it never crosses over 0. So that means that if we look at it, we have to test to see, well, then is it going to be positive or negative? If I square something, it's always positive. The top, it's never 0, so it's always got to be positive or negative. 2x squared plus 8, try plugging anything in there, always positive. So we have local max, none. Local min, none. Intervals of increasing. Negative infinity and negative 2. Negative 2 to 2. And 2 to infinity. Negative 2 to positive 2. That's where we have it. Okay, so that's what we're checking. And so if you don't see that, if you don't see what we just talked about, and just go right here. Just do like we did before. Plot your negative 2, plot your positive 2. Go ahead, plug in a value, and I promise you're going to get positive, positive, positive. Yes, we do have to do a second derivative. Because it's interesting because Derek would say, well, the second derivative, if the first derivative is never equal to 0, then surely the second derivative probably isn't. Actually, it's not true. The second derivative is going to be equal to 0 at one spot, and we'll see how that works out. Okay, so it's hard to know for sure the nature of that. So let's try the second derivative here. Okay, so I have 2x squared plus 8 over 4 minus x squared quantity squared. This is going to take a little while, okay? But we will persevere through the algebra. Okay, what is the derivative of the top? 4x, and we're going to multiply that by the bottom, which is 4 minus x squared quantity squared. Minus the top left alone, which is 2x squared plus 8. Very good. We got to chain rule the bottom. No, it doesn't really take too long. Chain rule the bottom. What's the derivative of the inside? Negative 2x. The derivative of the outside, I bring the 2 out front. 4 minus x squared, that's the inside. And we reduce the exponent by 1. So we just end up with that. Yep. So we have negative 4x times 4 minus x squared. All over the bottom squared, which is 4 minus x squared, quantity squared. All right, we're going to have to write out the top and try to simplify this a little bit. Well, fourth, yep, sorry. Fourth power. Oh, no, squared is right there. That's correct. Yep. Yeah. So Derek sees something very helpful right away, you guys. This has a 4 minus x squared, correct? This also has a 4 minus x squared, correct? And I have a 4 minus x squared in the denominator, correct? So let's factor out a 4 minus x squared and get 1 to cancel so we can get rid of it. So on the top, I will list that as 4 minus x squared. So I'm going to take that 4 minus x squared out, and I'm left with 4x times but it's multiplied by the 2x squared plus 8. This right here. Yeah, times a negative 4x. Okay, so 4 minus x squared times 4x times. We're left here with just a 4 minus x squared because we took one of them out. Minus, we have a 2x squared plus 8. Times only negative 4x, correct? All over 4 minus x squared to the 4th. Now, that's to the first power, so we can take one of them off to get rid of this, right? Well, I'm going to cancel one of the top one with one of the bottom ones. Okay. So, 4x, let's distribute this top, so we'll cancel this off with 1 on the bottom, reducing it to 3. So it looks like we're going to have 16x minus 4x to the 3rd. And then I need to distribute this negative 4x plus 8x to the 3rd. And plus 32x. Positive 4x to the 3rd. Plus 48x. Right? Very good. That's my second derivative. Question. Yes. You don't have to simplify. You could just do the top equals 0 right at the beginning. Because I'm guessing that, first of all, I wouldn't, you could do it like that. I wouldn't. I would simplify it. Because what I want to do is I want to be able to plug this into my calculator. I feel like I'm less likely to make the mistake. Second of all, I want to be able to solve where this is equal to 0, so you guys can either solve from the beginning or at the end. Either way, you got to do the algebra. So it's just really how you want to organize your work. So You don't have to, but that's what I would choose. So if we look at this, the top, boys, quiet. I'm wondering where the top is equal to 0. If I solve the top equal to 0, I take out a x. Sure, take out a 4x. 4x times x squared plus 12. No, now I'm solving where this thing is equal to 0. 0, and does x squared plus 12 have a solution that's real? No, so you only have one solution, and that's at 0. So the top is equal to 0 at 0. The bottom is undefined at... Bottom will give us an undefined answer again at positive 2 and negative 2. Have we accounted for the positive 2 and negative 2? Yes. So now let's draw... So the original function is undefined at positive 2 and negative 2. We know that the derivative is undefined at positive 2 and negative 2. We know that the second derivative is undefined at positive 2 and negative 2. That all makes sense. Now, the first derivative does not have a spot where it's equal to 0, but the second derivative does have a spot where it's equal to 0. Well, kind of. Let's now test our intervals to see whether or not we're increasing or decreasing in our type of concavity. We've already done the increasing. We know we're increasing 100% of the time. Let's test concavity. Okay. So what number to the left of negative 2 can you plug in? Negative 3. And we plug that into which one? Second derivative. Right here. In order to test concavity, I plug in negative 3 in the second derivative. So I have 4 times negative 3 to the third plus 48 times negative 3 over 4 minus negative 3 squared, or 4 minus 9 to the third. What's negative 3 to the third? Negative 27 times 4 is negative 108. Okay, 48 times negative 3, negative 144, over negative 5 to the third, negative 125. Are you going to come out with a positive or a negative? You will come out with a positive. A negative or a negative is a positive. So your second derivative right here is positive. What number would you like to check between negative 2 and 0? Negative 1. If we check negative 1, we have negative 4 minus 48 over. It would be 4 to the third. You get a positive or negative result. Negative. Now what do you want to plug in? 1. If you plug in 1, you get 4 plus 48 over 3 to the third. That is positive. And if you try 3, you get, again, we get the 27 times the 4 is the 108 plus 144 over 4 minus 9 to the third, which is going to be, it's going to be negative. Let us now write down our intervals, and then let's sketch this thing. Is it ever decreasing? Concave up. Negative infinity, negative 2. 0 to 2. Concave down. Inflection point occurs at 0. Plug in 0, you get 0. Here is my graph. I have vertical asymptotes. Now I have a horizontal asymptote of 0. I don't have to draw the horizontal asymptote in between because the horizontal asymptote represents the end behavior. This is the middle behavior. It can cross the x-axis in the middle, but it can't cross it at the end. If I am concave up and I am increasing, is my graph going to be in the top one or the bottom one? Top one. Let's go to the far right. If I'm increasing and concave down, am I going to be in the top one or the bottom one? Bottom one. Well, you have to follow the asymptotes. Okay? So it's either going to be like that or like that. Well, if you're like this, you're going to be decreasing and you're going to be concave up. If you're like this, you're going to be increasing, you're going to be concave down. It says increasing and concave down, so that's what we want to be. The last one, I have a concave down here, and I'm increasing. So we would have to have that shape. Crosses through 0, 0, and it changes concavity to all of a sudden being concave up. And you can see it's increasing the whole time. That would be our shape.